Hi and hello everyone. What we will do now is let us continue our discussion of MM1Qs that we have seen. So, we have obtained the equilibrium system size distribution in the previous lecture by three different methods. That three different methods you remember, because that is what is applicable for different queuing models depending upon the situation, depending upon the convenience that you will apply any of them to get the solution. Okay. Now, just recall that this is the Pn which is equal to this is what is the solution that we have obtained, which has the equilibrium solution for the MM1 system size probability. So, many a time it will be simply referred to as the equilibrium solution for the Q. I mean, for the Q we simply mean it is always that it is the system size distribution that is of interest for us. Okay. Now, let us look at certain performance measures to get, so that we can tell more about the system on hand and depending upon the quantities of interest, right. So, that is what one calls as performance measures, like you have the distribution and from which we are trying to obtain these quantities, right. First, what we will pick it up is this random variable n, which represents the number of customers in the system in equilibrium, and its distribution only we have obtained. Now, if you denote L as its expected value, then L would be equal to expectation of n, which by definition is equal to this quantity. So, if I plug it in here, for Pn 1 minus rho times rho to the power n, then I will get this one, but this series or this summation, if you look at here, right, this is typically we will use all these power series expansions and it is for different quantities, right. So, the geometric series expansions in a way. So, if you look at this is what you have as the form, which is exactly equal to this in the expanded form, which is equal to the derivative with respect to rho of this particular series, but this particular series you already know it is 1 by 1 minus rho, and hence this is equal to 1 by 1 minus rho square. So, we simply substitute that to get this rho by 1 minus rho, which again, since rho is in this particular case is lambda by mu. So, if you substitute, then you will get lambda by mu minus lambda. So, whether in terms of rho or in terms of lambda and mu. So, this is what is your expected system size as the average system size that one gets to observe. Now, similarly, instead of mean, I can also obtain variance, but for which first you need to obtain expectation of n square. So, essentially n square here, right, you do a similar, so what is simplification of that expression, and finally you will arrive at this particular quantity, right, this particular quantity, and because expectation of n square is this, variance of n would be this minus this square, right. So, that will give you variance. So, remember mean is rho by 1 minus rho, variance is rho by 1 minus rho square. Okay. Now, from Little's law, as we know, now the expected steady state system waiting time or the waiting time in the system for any particular customer can be obtained through Little's law as through this W equal to L by lambda, which will give me this, right, which is equal to 1 by mu minus lambda in terms of this, which can also be written in this form. There is a convenient reason as to why this particular form is also useful. Whichever way it is what is the expression that you can easily obtain, right. This is not a very complex expressions, all of this. So, we obtain this. Okay. Now, the purpose of getting these performance measures is typically to analyze the sensitivity of these performance measures with respect to the parameters of the model. That is what we will exhibit now, but this we will not do it for every other parameters, but that is what typically done when you want to analyze the performance measures. This is what in performance modeling of the systems, what one does is that you try to analyze the sensitivity either analytically if it is possible. Say for example, I can look at now how L behaves as a function of rho, right, or as a function of lambda alone, right, if I have this expression. So, I can try to get analytically like okay, what is the change in L if I change lambda, what is the change in the variance if I change my rho, what is the change in the expected system time if I change the lambda and or mu and so on, right. So, this is what if analysis that one needs to do, and for the purpose only you try to obtain this kind of simplified measures rather than dealing with the distributions themselves. Okay. Now, if you do this for this particular quantities of L, that is mean number in the system, and W, mean waiting time in the system, as a function of rho, if I look at what is that behavior, its behavior will be of this nature. Okay. So, you could see for both, right, probably up to 0.8 or something like that, you are in a good position, right, your things are not exploding in any sense. Whereas, beyond a certain point and very close to 1 for rho equal to 1, what you are observing is that both L and W grow in an unbounded fashion, right, in an exponential increase is what you, and this behavior is characteristic of almost every queuing systems. It goes without saying, we will not analyze it as it already for every system, but this is what one does with respect to a system if you want to analyze the system better, right. No, if you know exactly, because if you know exactly rho, you know exactly what is L, that is what you will obtain it here, right, by using this formula simply. But you want to analyze, right, basically that is what you want to do a performance analysis of the system, means that in terms of model parameters, how these performance measures behave is what is the objective here, right. Now, also as rho tends to 1, we also see that because P naught, which is 1 minus rho, it also tends to 0, which means that it is, you have very low probability of system being empty, right, and also variance of n is also exploding. What is the meaning of this? Large variance means what? What is for the system it means? The large variance means, right. So, if it is large variance, which means if it is a variance is small, of course, right, what is the expected system size, and that is what you get to observe at a random point of time whenever you are observing the system. Now, if the variance is large, what does that mean? That means that the expected system size behavior that you are giving here as an expression, as a value, you will not be able to see that most of the time, because variance is large. What will happen is that the size that you actually see in the system is likely to be very much different from the expected size. That is what the implication of large variance, right. So, if that is the case, that means that system predictability degrades in such a scenario, right. If the variance is small, I mean that is why this variance quantity plays a role in any statistical study, that because if the variance is small, then you have data which will be clustered around the mean, then mean will be a good measure to see, right. But if the variability is large, then the data will have values which could be very much different from the mean, right. That is what is implication, and that is precisely like here also you would find, if the variance is large, then the system predictability degrades. That means then there is a large variation in the number of customers in the system that you get to observe at different points of time, and hence you need to account for it if you are designing the system, or if you want to do analysis, or if you want to make any improvement in the system. So, that is all you have to keep that in mind. So, you need, because of this grows exponentially. It is like for values beyond 0.98 or 0.99, of course, you would like to use that, because then you will see that you are trying to use the server to the maximum. That is what you are trying to do, right. But that comes at a cost where both this is are degrading. The system predictability degrades, this mean number in the system explodes and hence the mean waiting time in the system. Whether that is desirable, you have to see, you have to find an appropriate balance for this row in that particular case. And also to analyze systems which are very close to 1, which are all generally known as heavy traffic analysis is what is employed, right. So, this row is what is your traffic intensity, right. So, row near 1, you need a very sophisticated theory to analyze how quickly it goes, what is the rate of increase that has happened in the particular system, right. To analyze all those things, you need a very sophisticated advanced theory, and that is what is called the heavy traffic theory or heavy traffic analysis of queuing system. So, there is a separate analysis that one can do with row very near to 1, and that is required because of this observation that you are going to make, right. So, this kind of behavior is typical of almost every queuing system that you would see, but we will not analyze it in such details, but this is the first model, like what kind of analysis that one can do with respect to your performance measures is what we are trying to show with this kind of behavior here. Of course, this whole thing can be shown analytically as well, right, but it is much more appealing if you can exhibit it through such analysis, such graph, it is very appealing to right. So the similar kind of thing you can do with every performance measures, that how it is sensitive with respect to parameters, but we are not going to take that up, but that's we will leave it. We will try to obtain the performance measures. One other performance measures, right, is basically this LQ, which is nothing but the expected value of NQ. What is that? So, this is the number in the queue in steady state, which means we are excluding the one who is in the service. So, this one, if I want its distribution is that 1 less in a way, right, if I want to see. If there are 3 in the system, that means in the queue there is at least there is exactly 2. If there is 10 in the system, that means there is 9 in the queue, right. These probabilities are the same, right. So, its expected value will be like n minus 1 times Pn is what then its expected value. So, which is basically equal to this, which can be written, right, from here this is a L and this is 1 minus P naught, right, you can write, but this equality holds for all single channel 1 at a service time queues, which we have seen earlier as a general result, right. Now, we know what we have computed L, so you substitute it L, 1 minus P naught is also rho. So, you get this expression rho square by 1 minus rho. So, L was rho by 1 minus rho, L square was rho square by 1 minus rho, which is in terms of lambda and mu is this. Again, you can analyze this L, but sometimes what is of interest is that the expected queue size of non-empty queues, given that there is queuing, then what is the expected size of the queue, right. So, which is we denote it by LQ dash, where what is my LQ dash? LQ dash is expected value of NQ given that NQ is non-zero. So, that means exactly the same as where Pn dash is the conditional probability distribution of n in the system given that the Q is not empty, right. And what does that mean? That means Pn dash is equal to probability of n is equal to n and the Q is not empty means there is at least 2 customers in the system. Right, there is at least, if there is 0 customer in the system, both system and queue is empty. If there is 1 customer in the system, the queue is empty, but system is not because he is getting served. If there is 2 customer in the system, that means that at that moment one is in the service, the other one is in the queue. So, there is a non-empty queue is there, right. So, that would require that your capital N is greater than or equal to 2, right. And given that this is the case, then what is the probability that n is equal to n? This is what your Pn dash. So, this will be then will be a truncated distribution, truncated to excluding the points 0 and 1 in the usual geometric one, right. That is what you will get. So, that is what you are going to get here. So, this probability, this conditional probability is same as this divided by this, but what is this quantity? N greater than or equal to 2 and n is equal to n is simply Pn for n greater than or equal to 2, and this quantity denominator is basically summation 2 to infinity of Pn, which is you can show it to be rho square, which is basically 1 minus P naught minus P1 is what you have to compute, and you will compute this to be rho square, and this is Pn for n greater than or equal to 2. If you assume that n is greater than or equal to 2, then this is same as Pn here. So, Pn by rho square is what these probabilities are. So, if you are interested in this kind of probabilities, then this is the distribution, right. Now, one can talk about its mean. That is basically this is what is the quantity here, and that is what we are obtaining it here is 1 by 1 minus rho is what the expected Q size of non-empty Qs, but if you want the distribution itself, then this is what is given by P n dash, right. So, this is truncated distribution, a truncated geometric distribution, truncated from the point 2 excluding the points 0 and 1, right. So, this is one of quantity of interest. Another performance measure of interest is finding the probability that system is loaded with at least a particular number of customers. So, what is the probability that n greater than or equal to 2, right, we have seen here. Similar things here, that is this is what it is. So, if you are looking at what is the probability that at any given point of time in equilibrium, what is the probability that the system will have at least 10 customers, at least 20 customers. So, it is at least n customer, that means this probability is equal to rho n, which again you can sum it up the tail of this geometric distribution, and from the geometric sum you can obtain this quantity, right. So, this is not a very difficult one. So, you can do that, right. Now, from Little's law, then one can look at now the steady state expected delay WQ, which is the expected waiting time in the queue, because LQ we already know. So, from Little's law applied to the queue, then we will get this quantity, right, LQ by lambda, which is equal to this, which is equal to this quantity. Again, you can analyze what will happen to this probability as rho tends to 1, and what will happen to, for example, this quantity as rho tends to 1, and so on, like many things you can analyze in a similar way. So, all the above formulas are very simple and useful, but they were developed, keep in mind that they were developed under specific assumptions of Poisson arrivals, exponential service time, and whatever assumption that we have made with respect to MM1, and also the steady state condition and Q stability to exist, that is what we are assuming. So, the transient effects or temporary effects are not captured by them. By that what we mean is that, suppose if you are looking at an airport and there is some kind of weather not good for flights to land at that particular point of time. So, the temporarily what you will see that this rho less than 1 may not be hold true. So, there will be some congestion, that is what will happen in the queue, the system, right. So, those things and all it is not captured by the equilibrium analysis, right, but then the arrival rate, service rate, things will get changed. That is only temporary though, but still one cannot handle that. So, this kind of analysis is very smooth, a first level, things are in equilibrium and there is no abnormal behavior happens, right. So, transient effects, which means when you start the system there may be some hiccups, right, to get the system moving and then comes to a steady state. So, basically what you have is that the steady state condition is established, after that then all these results will hold true, right. That is what you have to keep them. These are the constraints one needs to keep in mind whenever any mathematical model, any analysis that you do with your mathematical model is only an abstract of essential features of the real system, and the underlying assumptions have to be validated or kept in mind while trying to apply the results. If that is not done, then you will not be successful in applying the mathematical model to any real system. So, that basic principle holds here for all the things. So, you always have to keep in mind that the underlying assumptions that we have with respect to this. Okay. Now, we will see now like some more distribution of waiting time distribution in equilibrium, but before we do, like this kind of queuing systems with the Poisson arrivals have an interesting property which we will use quite often in all our analysis. That is what is called as the Poisson arrivals C time averages. Poisson arrivals C time averages, or in short pasta property. So, we will simply call pasta property. So, this is an interesting property, and what does this mean is that this means that an observer from a Poisson arrival sees the same system size distribution as a random observer from outside. So, at a random point of time you look at the system, at the arrival instance where the arrivals happens according to a Poisson process, at the arrival instances you look at the system, and looking at the system at random points across the timeline, this behavior of the system will be exactly the same, and that property is what this pasta. So, basically what we mean, for Poisson arrival streams we have an equals Pn. Pn we already know is the probability of observing the system at a random point of time, right. It does not specify at what time you look at this and then you will get to observe n in the system. The system is in equilibrium and at a random observer at a random point of time you are looking at the system is what will give you the probabilities Pn. An is basically the arrival instant observations of the system and the corresponding probability is what this An. So, An is the probability in steady state that an arriving customer finds n in the system just prior to arrival or upon arrival, right. Just prior to arrival or upon arrival is we will take it as a one and the same. So, just prior to arrival, at the arriving instant he finds n in the system in steady state is what this An. Okay. Now, this one is true, An equal to Pn is true provided this is two conditions. One is the Poisson arrival streams is what is required, the other one is the state of the system changes by at most 1, means you do not consider bulk arrivals, bulk series, this kind of the bulk arrival things is we are not considering here, right. So, if the state of the system changes by at most 1 and the results holds in transient state as well, means that An of t, even if you look at it, the corresponding it will be equal to Pn of t for all t greater than or equal to 0 as well. So, that is also true. So, even in transient phase you will get to observe this. Okay. But here when we see there is nothing else happening to the arrivals, all the arrivals are getting into the system and then they get served and they leave, that is the situation that we are assuming, which happens in MM1 situation, right. So, how do we determine An? We use Bayes theorem here. So, basically An is what? Probability that you get to observe n in the system and arrival about to occur at the arrival instance. So, this by Bayes approach, if you adopt, this is basically probability of arrival about to occur given that there is n in the system multiplied by this n in the system which is Pn and the sum over all these possibilities for different n's, right. Now, we know from our theory that probability arrival about to occur and when system size is n is nothing but lambda time in a small interval of length delta t if you are considering. So, this is equal to lambda times delta t plus order of delta t, right. There is one arrival in an interval of length delta t is what we are considering, right. So, that would be equal to this quantity which we already know and then Pn and this divided by, so this is also like exactly same quantities, now delta t tends to 0. So, this is what is this probabilities, right. That is what we have defined it also, there is a limiting quantities of this kind of things. Now, what you do? You divide numerator and denominator by lambda t, by delta t, then you will get this term will give order of delta t divided by delta t, which as delta t tends to 0, right. So, this will leave with only lambda. So, the numerator will have lambda times Pn. So, the denominator will have lambda times Pn, sum over n is equal to 0 to infinity, which is equal to 1 here. So, this lambda, so this will end up with Pn. So, this is what you see here, that An would be equal to Pn when. So, it is basically the independent increment property of Poisson process that makes this whole true, right. That is what we have. So, by pasta, in that case what we mean is in a queue with Poisson arrivals, the limiting proportion of arrivals that find the system in state n, arrivals finding the system state in n is what is this An is equal to the limiting proportion of the time the system spends in that state n, right. So, the proportion of long and proportion of the time system spends in n is what is Pn. So, the equality of these two is what we mean when we say pasta property. So, pasta property means the equality of ANs and PNs, right, that is what you have. Okay. So, this is what is pasta property, which is what we will use it now, where we will use it in this computation. We want to know what is the waiting time distribution. Recall that TQ is the time spent waiting in the queue in steady state, and f TQ of t be its CDF, okay, right. And we are assuming that the queue is FCFS, because till now we did not worry about that, but for waiting time distribution this is required. What is the queue discipline? That plays a critical role, as you will see. Now, AN, as we already know, is the probability that an arriving customer finds n in the system. And if you look at here, this FQ of t is the cumulative distribution function, and FTQ of 0 is basically probability that TQ less than or equal to 0, because you do not need to wait in the queue, which means you directly get into the service. For all those customers, like you would find the waiting time in queue is 0, right. So, which means which will happen when system is empty at an arrival, which happens with probability A0, because A0 is the probability that you find on arrival the system is empty. But these Pns and Ans are not in general equal, but as we just shown for Poisson input process, Pn is equal to An by pasta property, right. And that means this A naught is equal to P naught, which is equal to 1 minus rho. So, this FTQ naught is at the value 0 is equal to 1 minus rho. We now need to determine this quantity for t strictly greater than 0, right. Now, for which what we need, you observe that if there are n units in the system upon arrival, now if in order for this arriving customer to go into the service, right, at a time between 0 and t, if I want to fix a t here, and if I want to look at the probability that this goes into the service, that means what would require? Then the all n units who were ahead of him at the point of his arrival has to be served by time t. That is why this discipline is important, how the service takes place from the customers waiting in the queue. So, if he has to go to service at a time between 0 and t, only when if he goes to service between 0 and t, so we are computing probability of TQ will be less than or equal to t, right. Then all n units who are ahead of him, or customers who arrived ahead of him, must have been served by time t, right. So, since the service distribution is memoryless, so the distribution of time required for n completions is independent of the time of the current arrival, because currently a customer might be getting served. So, what was his remaining service time is exactly same as the original service time. So, and hence including him in the service, so there are n ahead of him. So, the total sum service time is given by the convolution of this n exponential random variables, each of them with parameter mu, and hence this has a gamma distribution with n mu, right, with n and mu as the parameters. Also note that an equal to Pn, two things we noted. So, we are looking at now f TQT for t strictly greater than 0. So, that would mean exactly equal to this is by definition. Now, this would mean that there is a mass at 0 plus for any t strictly greater than 0, right, if it has to be, there has to be n. So, if there is a strictly t greater than 0 strictly means that he has to wait, right, that means there is at least 1 in the system. So, there is at least 1 in the system, and or in general there is at least n in the system where n is at least 1, and this n service completions happens by the time t, so that he get into service by time t, right, and on his arrival he finds n in the system with the corresponding probability of an, but this since an equal to Pn, we can directly substitute Pn here, right. So, this is what is the argument. This is the argument that you need to remember, that you need to understand little bit more carefully how we are writing down this, right. Fq of 0, because there is a 0 weight, and if there is a positive weight, right, that means there is at least 1 in the system. So, he finds at least 1 in the system, and whatever number that he finds, all their service completions happens by time t, right. So that he gets into service by time, right. So that is what you have here, that is what you are writing it here in this condition. So now you just have to plug it the values. What is Pn's? Pn's is 1 minus rho times rho n, and what is n service completion, which is a gamma random variable with parameter n and mu. So this is the density of the gamma parameter with n and mu, and 0 to t is what that random variable less than or equal to t. So you just have to simplify this. Now what one can do, 1 minus rho here. So this 1 minus rho and this mu I write it here, right. 1 rho I will take it out. So I will keep this, the remaining rho I will push it inside. So I will get rho mu x to the power n minus 1 by n minus 1 factorial. This one is a geometric series, right, is 1 by 1 or e to the power rho mu x. Now you plug it that with e to the power minus mu x. So you will get this quantity. So this is what you get here. Now you observe that this is the exponential. This is again an density of an exponential random variable with the parameter mu times 1 minus rho. So you know what is this quantity is. So in that case this quantity is 1 minus of e to the power minus times mu times 1 minus rho times t is what then you will get, right. So that you plug it in, you will arrive at this expression here, okay. Expression here as the waiting time distribution of the waiting time in Q. Okay, so TQ, thus you see, is a mixed random variable. So there is a mass at 0 and there is a continuous distribution beyond that. So if I plot, for example, this distribution function, what you would see is that, suppose if this is time 0, right, what you would see, it is 0 up to this, of course this is all, and at this point it makes a jump, and from here it makes into this case. So this is what the jump height is 1 minus rho is what then you will get here, right. So this is the what you call f TQ of t, and this is t, right. So this is what you will observe in this particular case is what as this. So this is a random variable that equals 0 with probability 1 minus rho and follows an exponential distribution with probability rho. So it is a mixture of discrete and continuous. The discrete could be the 1 point degenerate random variable at the point 0, and that it takes that random variable with this probability and it takes this random variable with this probability. So that is what pretty much you have here. So 1 minus rho and the indicator that it is at 0, it is 1, and this is rho times an exponential is what then you are seeing it here. So that is what you will get here, right. Now we have obtained earlier this WQ, which is the waiting time in the queue, and which you can now obtain from this expression as well. So what is we know the result that the expected value is 1 integral 0 to infinity, this is a non-negative quantity. So 0 to infinity of 1 minus its distribution function times dt. So this one we already know. So 1 minus fq2 is simply rho times this quantity. So you integrate it, you will obtain it here. So you can verify that result, which is same as the one which we earlier obtained through Little's formula. But then the advantage of using Little's formula is that if you are not interested in the distribution of the waiting time, if you are interested only in the expected waiting time, then one need not do this analysis to obtain this distribution, right. But because in very complex situations like this will be very difficult to obtain, right. Waiting time distribution is maybe very difficult to obtain, right. So in that case, like if you are happy, if you are interested only in the average value, then Little's law can help you to get the average waiting time, right. And that is a great help in that sense, because when you are not able to do this, how you are going to compute the expected value of this distribution. But then Little's law helps you to do that. So that is where the power or the utility of Little's law comes into here. This quantity you can obtain directly without obtaining the distribution, that is what you would see. Similarly, by the exact same process, we can obtain the CDF of capital T, which is the waiting time in the system or sojourn time or system time, where a TQ is called as waiting time in queue or delay time, right, or queue time, whatever is what TQ. For T, it is waiting time in the system or system time or sojourn time. Okay. Now, this is an exercise. Only thing you have to note here is that if this whole system time has to be less than or equal to T, right, if he finds on his arrival n in front of him, then including himself, the service should be over by time T. So, you need n plus 1 service completion by time T. That is the only change that you have to make. Once you make in a similar argument, then you will obtain it here, which will now be a purely exponential. There is no mixed distribution here, right. So, it is a pure exponential distribution with parameter mu minus lambda, or mu times 1 minus rho, if you want to call it in that way. Mu times 1 minus rho or mu minus lambda is what the exponential distribution. So, the system time or sojourn time in a MM1Q is exponential, whereas the delay time in MM1Q is a mixture of exponential along with a degenerate random variable, right. So, these are, remember, because of this argument that how many service completion happens before this his service completion, we are looking at it, which we are looking at a typical customer who arrives at some point of time and when his service gets done, right. So, then Q discipline plays an important role, whereas the expected measures like this WQ does not need you can obtain W also from here, right, by using exactly the same distribution here, right. So, for those measures you do not need the Q discipline, but whereas for this particular analysis waiting time distribution you need the Q discipline. Remember, if suppose service in random orders, then what happens is that any time, suppose if there are 10 customers who are waiting on his arrival, you could imagine that any time whose could be his service or his or her service can start. That is the situation that you have at hand, right. So, then very difficult to obtain this. So, for that Q discipline, it is not going to be that whatever you obtain this is true, or last come first served, whatever is the case, right. It is again easier, but it is different from this, that is what you need to see, right. So, these results are applicable for a system in steady state. So, they are not applicable to the initial few customers who arrive soon after the start or beginning of this or opening of the system, right. So, system in equilibrium is what we are assuming, and in that situation this is what you get, because only when system is in equilibrium, the probability that you get to observe n customer in the system is Pn, or an arrival you find n in the system is En. If system is not in equilibrium, then that is not true. So, and hence the whole result will change, right. So, this is what you have to keep it in mind. Now, let us look at a simple example and see like what how these results can help us to analyze the thing. Okay. Suppose that there is a one person beauty parlor which is run by Ms. Deepa, and she follows an FCFS pattern, okay, first come first served pattern. So, she wants to analyze the performance of her parlor to serve her customers better, to make improvements to the system. So, what she does is that she does some bookkeeping to collect the data. So, she collects the data of different days in the week, how many customers come and whatever their service time, things like that she collects the data. So, and then from that she finds that the customers arrive according to a Poisson process with mean arrival rate of 5 per hour. So, on an average 5 per hour is what is the arrival rate, and the arrivals follow a Poisson process, which means that inter-arrival times are exponentially distributed. How she fits, how is an approximation, whatever you think, okay, that is what is the assumption that we are making it. The service times are also exponentially distributed with an average of 10 minutes. Okay. This is what is the observation. Of course, all the assumptions that we are having it with respect to MM1 holds true here also, you assume, right. So, that is what So, single person, so single server queue, Poisson process arrival and exponentially distributed service time is what is required. So, somehow like from the data, like this is what you get to know. Okay. Now, from the data we can see that lambda equal to 5, it is 5 per hour, mu is equal to 6 because each one takes 10 minutes. So, in an hour it is 6 per hour. So, it is mu is equal to 6. So, that gives you rho is 5 by 6, and hence using our formulas for L, LQ and LQ dash. So, L is 5, which means the average number of customers in the system is 5. The average number who is waiting in the queue is this one, say 25 by 6, and the if you have to wait, what is the average system size of customers, right, who are waiting in the queue? It's 6. Okay. So, the percentage of time an arrival can walk, so you can draw your own inferences from here, right, whether the L is 5 is good or bad, or depends on the context, depends on the situation, that we are giving the value. Now the inferences, drawing the inferences is for the person who want to analyze the system, right. So, the percentage of time an arrival can walk right in for service without having to wait at all, right. So, which happens, right, when there is no one in the beauty parlor shop, right. So, in that case, what, an arriving customer can directly get into the service, and for which the probability is P naught is, which is 1 minus rho, which is 1 by 6. So, every 1 in 6th customer on an average, again on an average, can get into the service directly. Okay. So, that means that also, this also means, right, P naught is the time that the server is idle, that Deepa is idle. So, 16.7% of the time Deepa is idle. So, a customer can get a chair without waiting. So, in other words, 83.3% of the customers must wait prior to getting into the chair, right. That is what we are seeing it here. Okay. So, which means that they have to wait. So, what is the probability that they have to wait is 0.833 is what then you are seeing it here. And also in the beauty parlor, like apart from the serving space which she does, and then there is 4 other chairs for waiting. The remaining customers, because she does a job so well that they do not mind waiting by standing. Okay. So, they stand and wait. So, means that only 4 people can sit. So, the waiting room has only 4 seats at present, and the customers have to stand when there is no seat. Now, if you want this probability that an arriving customer has no seat, which means he has to stand, that means the system must have at least 5, right, because 4 people who are already sitting, and the one is in service. So, n must be greater than or equal to 5, which is given by rho to the power n, which is this probability, which means that what, 40% of the time a customer, an arriving customer cannot find a seat, and also that the 40% of the customers will have to stand upon their arrival. This is what you get to see this. Okay. Now, again, if she wants what is the average waiting time, because we already know the parameter, so we can obtain that to be the average waiting time is 1 hour. The average waiting time in the queue is 5 by 6 hour, which is 50 minutes or so, right, and is good or bad, you have to decide. So, in general one would say that it is not good, because your wait is seem to be longer. Now, then if that is the case, I want to know like what is the probability that the line delay, means the time I wait in the queue is more than 45 minutes. If I want to know that, then I need this distribution, and from this distribution then I can obtain this to be equal to 0.39. So, close to 40% of the time the customers or 40% of the arriving customers wait more than 45 minutes is what then you are getting it here, right. So, that is what you obtain it. So, the last one, of course, you need the waiting time distribution, but if you are happy with this W and WQ, then you can go with that itself. But 45 minutes is too close to this 50 minutes, so that is why it will turn out to be that. Suppose if you are 15 minutes, 10 minutes, suppose if you want different time units, then you really need the distribution, and that is what you will get here, right. Now, we can seek answers to many other questions from our results. Of course, then we have to keep in mind our constraints that we have, which is basically MM1 system with all the assumptions that is inbuilt. Now, suppose the same data, suppose if you assume that it is represent the whole of week, means all 7 days data is what is putting together, it gives you this particular results, then the inference could be, again this is subjective again, but the inference could be that the Deepa needs to do some serious thinking of her service if she wants to make improvement, because either she needs to move into a larger space for people to get seat, because you see 40% of the people will stand, not even able to sit in there. So, she needs to put more chairs and also need to add a server, because people are waiting longer. Now, whether this much delay is acceptable is one has to decide. So, depending upon that she can make a decision in this case. So, that is how these performance measures will help us to make decisions of how on which direction that you want to make an improvement. Okay. But rather the same data, suppose if I assume is not the regular days data for say Monday to Friday, but the holidays Saturday and Sunday. Suppose the data that I have is with respect to Saturday, Sunday, or the original data is for all days. Now I segregate the data of different days separately, and maybe I can analyze separately whether in a particular day of the week things are working well or not. You can think about that, right? So, if that is the case, for example, Saturday, Sunday data, suppose the same data, suppose if I correspond to that on Saturday, Sunday, then what she can do, she may not be adding for the whole week the additional server, right, in order to reduce the waiting time and the number in waiting and so on. But then in that case, like this 4 seats might be sufficient also, who knows, right. So, but then she may, if the data is pertaining to only a specific days, then only on that particular day she may need to hire a part-time assistant. For example, Saturday, Sunday she can hire a part-time assistant to help her, so that this can be reduced. For other days, okay, suppose if that turns out to be okay, we do not know about the data. So, depending upon the data. So, these are the kind of thing that one has to do with respect to the data, what kind of data that you have and what you are getting out of it, and what kind of inferences that you draw, and what is the acceptable level. The quality of service is what we call it, right. The parameters have to be specified, so that this there is a balance between these two. We can only quantify the performance of the system through these performance measures by analyzing a queuing system, but it is up to the manager or designer or of the system to make a decision, which happens in like all business decisions. Like our job is to quantify and tell this is what will happen, this is what will happen. Suppose if rho is increasing to this is what will happen. If the rho is beyond this, then this is the number that you expect. So, it is all what if analysis that generally you refer to. That is what we do, but other than that it is up to the the manager, whoever is the authority to study or to analyze to improve the system, like he has to how he will use it. So, this all is a tool that is help us to improve the system. This is all we have for a MM1 system. We have given a broad overview which will be applicable across the different queuing models, but we will not analyze those queuing models in such details. The main points alone we will highlight, and we will try to obtain the quantitative measures is what would be our objective in the following the queuing models that we consider later on. Okay. So, but understand that MM1 model is so simple here, but it gives you so many insights to the system that how one can analyze it. That is the part that you need to go through carefully and understand the analysis of an MM1 system, so that it helps us to understand and analyze systems which are much more complex, right. Little complex or much more complex, the similar things are what we are going to do. Okay. Thank you. Bye.